the reset button on the board, okay, it actually sends reset signal, right? So that causes a microcontroller or processor to undergo reset. Otherwise, when you give power to the board, so it actually undergoes power on reset. So the first thing what happens when you reset the processor is the PC, that is the program counter, is loaded with the value 0. That's the first thing. Next, then processor reads the value at memory location 0 into MSP. All right. So the memory location 0 actually belongs to a flash memory or ROM memory, a program memory. Okay. So it reads the value which is stored in this location into MSP. So MSP is equal to value at this location. Okay, it's a 32-bit value actually. So MSP, which I will cover later when I discuss about stack pointers and all. But for the time being, just be aware that MSP is a main stack pointer of the processor. It's a register, a 32-bit wide register. So that means the processor first initializes the stack pointer. Great. So that's the second point. And the third point is after that, processor reads the value at memory location 0 cross 0 0 0 0 0 0 0 4 into PC. That value is address of the reset handler. So that means the address of the reset handler is put into PC. That means PC jumps to the reset handler now. Great, the PC jumps to the reset handler. Now, a reset handler is just a C or assembly function written by you to carry out any initializations required. And after that, from reset handler, you call your main function of the application. Okay, so that's how control reaches to your main function all the way from resetting the processor. So I have made a small animation for you here. First reset. Okay, the PC is loaded with address 0. And let's say at address 0, we have this value. Okay, 0 cross 2 0 0 0 8 0 0 0. Assume some value. So processor reads the value from 0 location into MSP. Now MSP is equal to this value. Okay. Next, then processor reads the address of the reset handler from the location 04. That means let's say 04 contains this value. So this value came to PC. And this is the address of the reset handler. So reset handler, let's say, is implemented here. So this is the first instruction of the reset handler. Okay. So the processor actually jumps to the address, this address that happens to be the address of the reset handler, and it executes the first instruction. Okay. Then you can call your main function from the reset handler, and that's how control reaches to the main. In the previous video, you came to know that whenever processor undergoes reset, it first fetches the main stack pointer value from the vector table, and then it jumps to the reset handler. And the reset handler address is also available in the vector table. Now the reset handler is usually implemented in the startup file of your project. Every project contains a startup file. If we open our project here, you can see that there's a startup file. A startup file contains a reset handler. That means this is the first instruction in this project which gets executed right after the reset. What's the job of reset handler? Job of the reset handler is to do some early initialization, and after that it calls the user program, that is the main function of the project. Then what are the responsibilities of the reset handler? Usually reset handler does initialization, such as data section initialization, BSS section initialization of a standard C library if it is used. Finally, it calls the user program, that is the main function. Without doing all this initialization, you cannot call the main function. The user code may not work properly. These are mandatory steps should be completed before calling main. In this course, I have introduced a section where we write the starter file from scratch. That means we write our own vector table, we write our own reset handler, and we do all these early initializations. And then we call the main function. Those are some advanced topics which I have introduced sometime later in the course. You will find those sections as you make a progress. But the key takeaway from this slide is very simple. You cannot call main function without these early initializations. That's why these early initialization codes must be there in the reset handler. When you created a project, your IDE has already added those early initialization codes. You can see here in the reset handlers, these are early initialization codes. Some code initializes the data section, some code initializes the BSS section. All these are initialization codes. And after that, finally, it calls main here, branch to main. Before that, it also does a libc initialization, that is standard library initialization, and a lot of other things. With that note, I would like to end this lecture, and I'll see you in the next lecture. In this lecture, I'm going to demonstrate switching between access levels. I have created a new project here, access levels. I'm going to my earlier project, that is operation modes, and I will copy the same code, paste it here. And now let me do some modifications here. First of all, the program starts with thread mode plus privileged access level, remember. Before calling this function, let me switch off the privileged access level. That means let's make the thread mode unprivileged. That's why I would write a small function, change access level to unpriv. Let me implement this function right here. Let's understand later how to change the access level. By changing the access level to unprivileged, I'm going to generate an interrupt. What happens here is when you go to the generate interrupt function, since the thread mode is in unprivileged access level, you cannot able to execute these instructions. You cannot change these system specific addresses of the processor. These have restricted access. That's why we should see a processor fault. Let's see that by executing this code on the target. First, let's understand how to change the access level. You know that to change the access level, you have to change something in the control register of the processor. Let's explore that. I am in the generic user guide, and let me search for control register, which is right here, control register. Here, as I explained in the earlier lecture, you have to make this bit as 1 to make thread mode as unprivileged. How do you access this register? So as I explained previously, this is a core register. This is not a memory mapped register. This doesn't come with its own address. You can't use your C pointer manipulation to access this register. You have to use pure assembly instructions. So we'll use inline assembly code. Anyway, you already know how to write the inline assembly instructions in a C program. First, let's read this register. After that, let's modify the value. And after that, let's write back. Let's use read, modify, and write technique. Let's get back to the code. How do you read the special register, which is control register? First, let's use MRS, read. I would use the first general purpose register R0, and after that, I would use control. Let's use our inline assembly syntax, ASM, volatile, and I have to keep this instruction inside the double quotes. We got the value into R0. After that, let's modify it. We have to set the 0th bit. For that, I can use ORR instruction, or this instruction you can again refer from to get the details of ORR instruction. You can go to data processing instructions. Here it is, ORR, logical OR. You can use this to set a bit. Destination, operand 1 and operand 2. That's a syntax. You can explore this document for more information. I would use destination as R0 or with, let's use immediate value 0 cross 0 1. Because my goal is to set the 0th bit. This is operand 1, operand 2, and the value after ORing will be put into R0. And after that, write back. For write back, you can explore MSR instruction. MSR, special register RN. Let's use MSR instruction. This is a place where we are changing the privileged access to unprivileged access. After that, the function returns here. And after that, the function enters generate interrupt. Now the code cannot access these addresses because these addresses can only be accessed by being in privileged access level. So now the code is in unprivileged access level. Trying to access those addresses will cause a processor fault exception. We are going to observe that now. That's why let's implement a fault handler. So don't worry about fault handlers. We have a dedicated section explaining faults and faults handler. I would just implement a hard fault handler here. You can observe that control comes to this fault handler, and I would trap the code here in an infinite loop. Let me just build this code. Let me just debug this code. Just observe the control register because we modify the control register. Initially it is 0, you can see here, and now let me just execute this and let's step into this function. Let's observe the value of R0. R0 is 10. Let me execute step into R0 is 0 because we read the value of control to R0. Step into, yes, R0 becomes 1 and control register modifies here. Let's observe the control register. This is a problem with the IDE. Control register value is actually 1. I'm not sure whether it's a problem with the IDE or the debugger cannot able to access that. So it should show 1 here actually. But let's assume that control register's value is 1. And now let's exit this function. Let's enter into this function. Here you can see that I'm trying to access this address, which only permits privileged access. Now I am in unprivileged access level. Just check what happens here. I'm going to execute this. Here it is. There was a fault. And so the control reached the hard fault handler. Here you can see that. If I just check the fault analyzer here, go to show view and fault analyzer, and you can see that it is actually a hard fault, bus memory management or usage fault. The exact cause of fault is usage fault. And now it is trapped here. Then what's the use case of this? Let's imagine an application which involves embedded kernel or real-time operating system. A RTOS-based project has two components. One is a kernel and another one is user task. So the user task should not affect or should not modify some of the system level settings of the processor. The user task should not trigger any interrupt or it should not turn off any interrupts. If that happens, then the whole system fails, isn't it? That's why before running a user task, the kernel can change the access level to unprivileged, and then it can launch the user task. That's why the real-time operating system or secured systems always launch user task in unprivileged access level. And if the unprivileged code wants any services, then it can trigger system call. And that system call will be serviced by the kernel code. That's a procedure or that's a design which is followed in a secure and robust system. And ARM Cortex-MX processor gives that features in the processor itself. By using those features, you can build secure and robust embedded software solutions. That's about switching from privileged access level to the unprivileged access level. The question is, how do you switch back from unprivileged access to the privileged access? How do you do that? Let's discuss that. Let's understand that with this diagram. First, processor started with thread mode and with a privileged access level. Control register was 0. And after that, you made control register 1. That means you moved to unprivileged access level. Once you are in unprivileged access level, you cannot go back to the privileged access level. That's not possible. Why? Because for the simple reason, by being in unprivileged access level, you cannot access this control register. That's a trap. Because to modify control register, you need privileged access level. That is one way you can go back to the privileged access level. That is to move the mode of the processor from thread to the handler mode. How do you do this? By triggering an system exception or by triggering an interrupt. Once interrupt hits the processor changes the mode to handler mode, isn't it? The ISR runs. As I said in the previous video, ISR always executes with privileged access level. Here you can modify the control register. Modify the control register back to 0 and then exit to thread mode. The thread mode will be privileged access level. Once you changed thread mode's access level from privileged to unprivileged, so to change back to privileged, you have to take this path. That's the only path available. That is, you have to trigger a system exception or interrupt, go to the handler mode and modify the control register there, and then come back to the thread mode. I hope you get the idea about switching between privileged access level and unprivileged access level. And that's it for this video, and I'll see you in the next lecture. In this lecture, let's discuss about T-bit of the EPSR. I'm going to explain what is the importance of T-bit of the EPSR. Various ARM processors support ARM thumb interworking. That means the ability to switch between ARM and thumb state. The processor must be in ARM state to execute instructions which are from ARM ISA, that is ARM instruction set architecture. And the processor must be in thumb state to execute instructions of thumb ISA. If T-bit of the EPSR is set, processor thinks that the next instruction which it is about to execute is from thumb ISA. And if the T-bit of the EPSR is 0, then processor thinks that the next instruction which it is about to execute is from ARM ISA. That's the use case of T-bit. T-bit decides what kind of instruction it is, whether it is from ARM ISA or Thumb ISA. The Cortex-MX processor does not support ARM state. Hence, the value of T-bit must always be 1. Failing to maintain this is illegal, and this will result in the usage fault exception. Because ARM Cortex-MX processor cannot execute ARM ISA instructions, because the instruction set architecture used in ARM Cortex-MX processor is Thumb ISA. We can only execute thumb instructions. When you are working with ARM Cortex-MX processor, the T-bit should always be 1. The LSB, that is bit 0 of